Hello students, welcome to Eduauraa. I am your physics mentor Umesh Nirgun, and today I would like to discuss the previous year question of the surface tension. And here is our first question. A spherical ball of radius r is falling into a viscous liquid of viscosity eta with a velocity v. The retarding viscous force acting on the ball is, and the options are A. Directly proportional to r but inversely proportional to v. Option B. Directly proportional to both radius r and velocity v. Option C. Inversely proportional to both radius r and velocity v. And option D. Inversely proportional to r but directly proportional to velocity v. It's a 2004 question. So let me discuss. Whenever we have a body or sphere, it is dropped into the liquid. After some time, when the total force acting on the body, it becomes what? Zero. It is moving with a constant velocity, that is called as what? Terminal velocity. And it is because of one force, that is called as what? Viscous force. Okay. And according to the Stokes Law of viscosity, the viscous force acting on the body is given by F is equal to 6 pi, which is constant, eta r v, where eta it is the coefficient of viscosity, r it is the radius, and v it is the velocity. So this viscous force, it is directly proportional to both r as well as v. Okay, so the correct option is option B. It is directly proportional to both r and v. Now we have a next question. A 20 centimeter long capillary tube is deep in water. The water rises up to the 8 centimeter. If the entire arrangement is put in a freely falling elevator, the length of the water column in the capillary will be, and options are option A 20 centimeter, option B 4 centimeter, option C 10 centimeter, and option D 8 centimeter. It's a 2005 question. So here we have a beaker consists of water, and the length of the capillary it is 20 centimeter. Okay, outside the water it is 20 centimeter. Now initially the level of water in this capillary, it is up to 8 centimeter. Now this entire arrangement, it is kept in the elevator which is freely falling. Clear? So what about the length of the water column? So it is a formula. Height of the water column or liquid column inside the capillary, it is given by H is equal to 2t cos theta upon r rho g, where g it is the acceleration due to gravity. Now suppose if it is kept in the elevator which is in the free fall, then I can say H is equal to 2t cos theta r rho in the bracket g minus a, where a it is the acceleration of the elevator. But as it is the case of free fall, the elevator it is moving in the downward direction, and the acceleration it is same as that of the acceleration due to gravity. So H is equal to 2t cos theta r rho g minus g. So it becomes 0. Any number upon 0, that is equal to infinity. So H is equal to infinity. So according to you, the water must come out of the tube, but it is not going to happen. Why? Because when the water it is going to occupy the entire length, after that there is no capillary action, and that's why during the free fall the water it is going to occupy the entire length. Though on the paper we are saying that it is infinity, but actually it is going to occupy the entire length. And the entire length of the capillary, it is given how much? It is 20 centimeter. That's why I can say the length occupied by the water, it is 20 centimeter. So the correct option is option A, 20 centimeter. Now the next question. If the terminal speed of a sphere of gold, density 19.5 kilogram per cubic meter, is 0.2 meter per second in a viscous liquid, find the terminal speed of the sphere of silver of density 10.5 kilogram per cubic meter of the same size in the same liquid, and the density of the liquid, it is 1.5 kilogram per cubic meter, and the options are option A 0.4 meter per second, option B 0.133 meter per second, option C 0.1 meter per second, and option D 0.2 meter per second. So it is given a gold sphere here. Okay, I'm going to drop this sphere in the viscous liquid. Density of gold, it is given, I can say rho of gold. How much? It is 19.5. It is dropped into the liquid. So it has some density. So density of liquid, it is 1.5 kilogram per cubic meter. And in this case, the terminal velocity, I can say V of gold, it is 0.2 meter per second. Now the second case. In the second case, we have the same viscous liquid. So I can say rho L, it is 1.5. But now I am going to drop the silver sphere. The radius, it is same. It is not going to change. The only thing is that the density, it is going to change. So I can write down the density of silver, it is mentioned. How much? It is 10.5. So what about the terminal velocity of the silver? Vs we have to find out. Now I can use the formula of terminal velocity. What is the formula? V is equal to 2 by 9 R square, density of solid minus density of liquid into G upon eta, where eta, it is the coefficient of viscosity. Okay. Now the size, it is remains same, so R, it is same. Liquid, it is same, so the coefficient of viscosity, it is also same. 2 by 9, it is constant. G, it is constant. So I can say V is directly proportional to the difference in the densities of the solid and liquid. So now I can write down V silver, velocity in the silver upon velocity in the gold. So that is equal to density of silver minus density of liquid divided by density of gold minus density of liquid. So now I can find out the velocity of the silver sphere in that liquid. So it is Vs, Vg, velocity in the gold, it is 0.2. Density of silver, it is 10.5 minus 1.5 in the bracket, divided by 19.5 minus 1.5. 10.5 minus 1.5. So it is 9. And 19.5 minus 1.5, so it is 18. So Vs is equal to 9 by 18 into 0.2. 9 by 18 means it is 1 by 2. So 0.2 divided by 2. So it is 0.1 meter per second. Okay. So the velocity it is 0.1 meter per second. So this question it is 2006 question. And I can say the correct option is option C, 0.1 meter per second.